Hi, my name's Oliver, and today in Lab 4 I'll be discussing the operation of photodiodes. The aim of this experiment was to first determine the IV characteristics of a photodiode at various light intensities. The aim of Part B was to sinusoidally modulate the LED in order to determine the frequency response. In addition, the LED was modulated using an input square wave, allowing students to analyze the effect of the output voltage as the period of the wave decreased. During this process, the rise time of this system could also be determined. So, a photodiode is essentially a semiconductor which, when exposed to light, generates a potential difference, or at a super basic level, converts light to electricity. To properly understand how this works, we must first take a look at the photodiode a little closer up. Begin by recalling that this PN junction is arranged in reverse bias, meaning that the holes and electrons are deflected away from the center, therefore widening the depletion region. Now, if the incident light consisting of photons has sufficient energy, larger than the band gap between the conduction and valence bands, then some electrons are able to absorb this energy, allowing them to jump up into the conduction band. When the incident light is brighter, it means more electron-hole pairs are formed per second, and so consequently, the total current through the circuit will increase. When an LED is used as a light source and the circuit is arranged as shown, we can expect a corresponding IV characteristic to appear like this. And so we can observe that as we introduce more light intensity, the current grows. Note that it becomes more negative in this context since the circuit is reverse biased. The photon energy at a particular wavelength can be simply calculated as Planck's constant multiplied by the wave frequency, which is equivalent to hc over lambda, where c is the speed of light and lambda is the wavelength. And so for a wavelength of 600 nanometers, we can sub in these values and determine the photon energy to be 2.07 electron volts. Phi is the photon flux, or the number of photons per second in a beam. The flux can be determined by dividing the power by the energy of the circuit. And so using our initially determined value, we find that the flux in a 1 microwatt 600 nanometer beam is about 3.02 times 10 to the 12 photons per second. The current produced in a photodiode at a wavelength of 500 nanometers can be determined by rearranging the following expression of power. Assuming the quantum efficiency is 100%, we find that the current produced would be relatively small value of 3.976 times 10 to the negative 16 amps. The real-world practicalities of this phenomena will be discussed at the end of this presentation. The rise time of a photodiode can be defined as simply being the time required for the photodiode to increase its output from 10% to 90% of the final output level. Additionally, using this value, the bandwidth can be determined by dividing 0.35 by the rise time. First, the provided oscilloscope data was imported and the channel 2 column was converted into current readings by dividing each value by the given resistance of the circuit. The voltage column was then multiplied by -1 in order to account for the reverse bias of the system. After applying the mean and standard deviation functions, the current was plotted against voltage. This was repeated for all 7 light intensities, and the hold feature was used to simultaneously plot and then plot them all together. The IV characteristics of the photodiode LED circuit could then be visualized. In Part B of the experiment, Channel 1 and Channel 2 were plotted against time in order to first get a general idea of the voltage gain, and any outliers were removed. Then, average amplitude of the output voltage was divided by the average amplitude of the input voltage in order to obtain the voltage gain. This was repeated for all 12 frequency files. All of these voltage gains were then plotted against frequency using a logarithmic scale to produce a frequency response. The processes were repeated for the case of a square wave. Finally, the rise time was graphically determined, from which the bandwidth could then be numerically obtained. Okay, so here we have the obtained reverse bias IV characteristics of the photodiode. As expected, when the intensity of the LED was increased, the photocurrent of the circuit was found to increase, or if you like, become more negative. Additionally, we can also see that when there is no LED present, i.e. this black line, there's still a tiny amount of current in the circuit within the reverse bias region. This is known as the dark current. This means that there is an element of noise during the subsequent measurements. Part A could be improved by repeating the experiment in a dark room to reduce the effect of unwanted light, which may in fact change throughout the duration of the experiment. So here we can see that the experimentally determined frequency response for the sinusoidally modulated LED circuit. And we can clearly see that the voltage gain begins to rapidly deteriorate at frequencies beyond 1000 Hz. Also, we notice a relatively stable gain for the frequencies smaller than this point, as expected. These results could be improved by repeating the experiment and investigating more frequencies closer to this drop-off frequency, allowing a closer and more accurate analysis around this point to be achieved. However, the results obtained in this frequency response failed to identify a clear resonance point, expected to be close to about 1000 Hz. This may be due to the fact that we simply didn't calculate enough data points close to this frequency point from which the voltage gain began to deteriorate. When the LED was modulated with a square wave, the output voltage became extremely distorted the more the frequency was increased, or if you like, the smaller the period was. So first we can take a look at the voltage gain for the 1 Hz signal, where pretty much no distortion is evident. We observe that the input voltage of 6 volts jumps to an output of about 12, yielding a gain of approximately 2. However, taking a closer look at the 1 kHz case, we begin to observe photodiode amplification becoming unstable, with rapid peaks occurring throughout each cycle. And so evidently, for each case as the period of the wave is decreased, more distortion occurs. In practical applications, adding a small capacitor can actually be added to the feedback loop to reduce the effect of gain peaking and prolong the stability of the circuit. By determining the time required for the photodiode to increase its output from 10% to 90% of the final output level, the rise time could be calculated. Using Excel, the rise time was found to be approximately 10 microseconds, which is actually relatively large compared to the expected value, known to be in the magnitude of nanoseconds. Using this value, the bandwidth could be simply calculated by dividing 0.35 by the already determined rise time, from which we obtained a bandwidth reading of 35,000. This experiment is significant because it demonstrates the underlying physics principles responsible for many real-world applications. These applications can range from autofocuses in your everyday camera to position sensors and surveying instruments used in industry. Thank you for watching this presentation.